Hey AI enthusiasts! Welcome back to All About AI Tech, your ultimate source for all things AI. Today, we're diving into a really cool project that's making waves in the medical world, HeartBERT. Forget those general-purpose LLMs that try to do everything but excel at nothing. HeartBERT is different. It's a specialized language model built specifically for cardiology and trained on a massive dataset of relevant medical literature. Imagine having access to the collective knowledge of hundreds of years' worth of cardiology research and a model that has a grasp of the technical details and terms that would baffle most other models. That level of detail is what makes HeartBERT so extraordinary and what makes it so useful. We will discuss all of these aspects of this specialized model, focusing on what makes it unique among the many other LLMs offered for deployment. We'll explore the innovative training methodologies and highlight the incredible potential for improving patient care and medical research. So, how did they build such a powerful model, one that outperforms others in its specific domain and use cases? The secret ingredient boils down to data, and the right data. Now, you might think, oh man, collecting lots of data in medicine must have been an impossible endeavor. And you'd almost be right. It's not enough to collect a mass of general documents. Those would likely also contain data that is totally irrelevant and can confuse the model. You'd end up with a model that is general purpose, but fails to deliver in the area you need it most. We need tons of data, but the data has to be highly specialized and relevant to cardiology. The researchers took a clever two-pronged approach. Who else would have thought of doing it? Using both PubMed and Wikipedia? Firstly, PubMed has become one of the standard resources used in medical research today, and it includes abstracts of high-quality research papers from experts in the field around the globe. The authors of these papers typically have advanced training, experience in their specialization, and their research needs to undergo a peer review process, thus ensuring a level of confidence and quality that other public resources normally lack. Of course, PubMed has information on medicine in general, hence they also needed to focus on extracting data specifically related to cardiology. For this, they used a very clever approach by using cardiology journal titles as queries in their API calls. This immediately cut down many of the documents that would have been irrelevant for them, greatly reducing the total volume of data they had to handle. They also used specialized glossaries. However, glossaries in any field also tend to include a variety of general terms, and not all that is in a cardiology glossary is necessarily specific to cardiology. Hence, after doing their initial query, they additionally spent considerable time reading through the initial results to get rid of any extraneous information by manually eliminating entries that were not exclusively cardiology-related. But what is the purpose of adding a second database? Besides PubMed's data of high quality and specificity, Wikipedia offered the research team a unique strength. Although not curated in the same manner as PubMed, by providing access to a larger, more diverse corpus, they were able to train a model that was better generalized. The researchers used Wikipedia's structured labeling to gather additional data. I'm simply amazed by their initiative here. Wikipedia proved useful in two unique ways. Starting from the top-level category of cardiology, they navigated through several subcategories and added these to their query, and also used their compiled glossary. That kind of initiative and dedication goes a long way in explaining what made their model so brilliant. I wish I'd had the time to do that while writing my undergraduate honors dissertation. That project would have benefited dramatically from this level of focused data collection. Now that we have a sense of how this dataset was created, let's move into the architecture and training techniques the team used to create such a powerful cardiology language model, HeartBERT. The researchers chose a model that's been shown to be extremely effective in processing language data, specifically BERT models. You probably already know about BERT models. They're designed to be pre-trained on general language data to understand context and generate rich information before being fine-tuned for a particular task or industry. That ability to pre-train and fine-tune models is what made this particular approach to language modeling so successful, and why it's become a standard for creating state-of-the-art language models. The process took advantage of two different sizes of BERT models, BERT-Tiny and BERT-base, both of which are well documented and widely available. This allowed researchers to study the impact of model scale in relation to its various performance aspects. This model-building approach reflects the structure of the medical world itself. There are a large variety of physicians, nurses, and other medical professionals with varying levels of expertise or skills. Using various models allows researchers to study not only how model scale and pre-training impacts performance, but it also allows us to directly relate particular model skills to particular professional responsibilities and expertise. But how many models did they train, and how much data and compute were required to produce such impressive results? There were a total of 8 models trained, built by exploring all combinations of two model sizes, BERT-Tiny, BERT-base, two training approaches, Scratch, Continual, and two datasets, version 1 containing PubMed, version 2 containing PubMed and Wikipedia. The researchers used two primary training approaches. The first, called continual pre-training, involved further pre-training pre-trained BERT-Tiny and BERT-base models with the cardiology-focused datasets. Essentially, this is a fine-tuning approach that does not change the architecture of the pre-trained model, just adjusts a pre-trained model's parameters based on new data and knowledge. The second approach, called scratch training, involved creating a language model from scratch, starting from a random initialization of the BERT-Tiny and BERT-base models' parameters and their core architecture. These two training approaches created a series of models with various strengths and capabilities, enabling the research team to study the impact of various training practices in relation to the data used and the model size. Let's dive deeper into the training process in order to better understand how this specific cardiology language model, HeartBERT, was trained. To build up their model's understanding of language and not need labeled data for this step, the researchers used the masking technique. You've likely heard about masking. It's been used in the pre-training of models like BERT and has been proven to be very effective in capturing the contexts that are necessary to interpret the meaning behind a passage. In essence, the masking approach involves selecting and randomly replacing certain tokens, or words, in a sequence with a special masking token, mask, and then training the model to reconstruct the sequence with those tokens restored to their original values. This is akin to a crossword puzzle, where the model is expected to fill in the missing words, the masked tokens, based not just on each word itself, but considering the position of the word and other words around it in the sequence. By masking tokens and training the model to restore them, the model effectively learns a larger context of language. It grasps grammatical patterns and word co-occurrences with particular insight into context. In this pre-training process, the model is learning to understand language without ever actually receiving any labels. By not relying on labels, the researchers ensured that their pre-trained models would not only have a better grasp of the world's knowledge, but were also protected from any particular biases embedded in certain datasets which can influence models trained on exclusively labeled data. Following that initial pre-training, this pre-trained model then undergoes fine-tuning. The aim is to adapt the model's ability to handle heart-related information by further training the model on a fine-tuned dataset annotated with information related to the cardiology domain. Fine-tuning is typically accomplished via supervised learning, meaning labeled data is required. As previously discussed, the researchers took considerable time and effort to prepare a high-quality dataset related to cardiology. Next, we'll consider the various choices the developers used in optimizing their model during training to produce enhanced performance. Now, everyone knows that there's a lot of knobs to turn when it comes to training a language model. It's essential to carefully adjust these hyperparameters, the settings that define the training process, if you want to ensure that the resulting model will accurately perform well. One of the most significant decisions is to select the appropriate optimizer. The optimizer is the specific algorithm that specifies how the weights of a given layer are changed in response to the error in its prediction compared to the ground truth value at every training step. By implementing the Atom optimizer, the researchers were able to generate gradients, i.e., directions in which you move the weights, for each parameter in the model, and adjust the weights to minimize the error across the dataset. As you might expect, there are various approaches to calculating this gradient. However, Atom has been shown to be a powerful and effective approach to optimization across various problems. This is why it's become one of the most widely used algorithms in machine learning today. Other important hyperparameters include the learning rate, which controls the size of the changes made by the optimizer at every step. You might already know what it means to adjust the learning rate in model development. Starting with a small learning rate ensures the model does not change too fast in early stages, minimizing the risk of overshooting the ideal response. Further, as the model learns over time towards well-trained weights, the learning rate is often decreased to slow things down. Reducing the step size in the later stages also helps to ensure that a model continues to improve, rather than getting stuck in a local minimum. Next, the authors made many careful choices that are consistent with the well-established practices of training language models. For both pre-training and fine-tuning, they set the learning rate to a typical low value of 2e-5 and used the popular GELU activation function. This selection of parameters was based on a series of exploratory experiments comparing the performance with various parameter values, detailed in the supplementary information, and were intended to ensure reasonable training speed alongside reasonable model convergence. For both pre-training and fine-tuning, the researchers established a warm-up period where the learning rate increased linearly towards its maximum value before gradually decaying. a commonly used technique in deep learning to improve the stability of training. Finally, for pre-training they used a batch size of 2, meaning at each step of training, the model is presented with only 2 sequences and then updates its weights accordingly, while for the fine-tuning they used a larger batch size of 32. This selection again takes into account well-established norms and practices around training language models, balancing the need for fast training with the requirement for a computationally robust learning process. With these parameters and more, detailed more thoroughly in the supplementary materials, the authors were able to generate impressive results. The research team meticulously evaluated not only the performance, but also the efficiency and suitability of the 8 different models for the pre-training and fine-tuning exercises. The outcomes are reported using a variety of traditional measurements of machine learning success, and several insightful observations emerge from their findings. The performance across each of the models was measured using the MCC, Matthews Correlation Coefficient, a score that assesses model accuracy on a binary classification task. This is highly relevant here, given that the goal is to measure the accuracy of predicting whether or not a given text snippet contained information about cardiology. This metric is ideal to use here, given that the model also included both true and false labels for each training instance. The higher this score is, the more effectively the model can distinguish and predict whether or not something is related to cardiology. In these experiments, the model with the highest MCC across all the datasets and experimental settings involved is the BERT-base, continual Ver2 model, which is trained using the continual pre-training approach with both PubMed and Wikipedia data. Its scored is 0.93, which shows excellent model accuracy. Now, let's explore what this means more concretely. This score means that, given a completely new excerpt of text, HeartBERT is very reliable in correctly differentiating whether or not the excerpt has a relationship or association with the field's core knowledge base. This ability to accurately distinguish cardiology-related information is exactly what makes HeartBERT so powerful. Moreover, by also evaluating model performance on several downstream tasks, such as named entity recognition, NER, we also gained insights into how well each model could extract a wider range of cardiology-specific information from new snippets of text. This is especially interesting because even this simple NER task requires not only the model to grasp the specific meaning of the words, but also understanding some or all of the context of the passage. The results provided in the supplementary information show that both the BERT-Tiny and BERT-base models perform much better given the continual pre-training approach, compared to models trained from scratch. This indicates that fine-tuning, which leverages pre-trained models to adjust their parameters based on new data, is a more efficient and effective way towards improving the accuracy and effectiveness of extracting knowledge from new corpora. In conclusion, this research study presents a significant advancement in the field of cardiology-specific language models. By carefully curating a specialized dataset from PubMed and Wikipedia and employing innovative techniques for model training, the research team was able to develop HeartBERT, a model that has surpassed the performance of related models currently publicly available in the field and has achieved high accuracy in capturing the salient features of cardiology-related texts. The use of both pre-training and fine-tuning was shown to be an effective strategy in improving performance, showcasing the value of leveraging the capabilities of pre-trained models like BERT. The findings highlight HeartBERT's ability to provide highly accurate classifications of cardiology-related terminology and its potential to aid in various medical applications, especially those related to medical document comprehension, such as quickly identifying relevant sources of information for diagnosis, research, and providing patient support. Furthermore, the research emphasizes the importance of carefully selecting and pre-processing data for effective training. By combining insights about model architecture, training methodologies, and data selection, this study paves the way for developing specialized language models tailored to specific use cases across industries. Considering the expanding capabilities of AI, and the high-quality and domain-specific data available, this research effort serves as a cornerstone for further research and development by demonstrating what is possible when creating a language model specific to a domain for a certain professional purpose. This accomplishment in medicine serves as an example for various organizations in a multitude of industries seeking to create highly focused models adapted to their particular domain needs, and I strongly believe that HeartBERT will substantially impact the treatment, efficiency, and quality of care in the cardiology field. I genuinely encourage you all to check out this fascinating research. The paper itself is publicly available, as are the datasets. I'd love to hear your thoughts in the comments. Let's keep pushing the boundaries of AI and its potential to improve healthcare.